Welcome to solverfy.
So we have to the left a diagram of the system, and so we should first use Bernoulli's equation. We're going to say that the atmospheric pressure plus PGH sub O plus 1/2 rho V sub O squared plus P sub 1, rather, this equals P sub 1 plus PGH sub 1 plus 1/2 rho V sub 1 squared. We know that the P sub 1 is going to equal the atmospheric pressure. So we can say that P naught minus the atmospheric pressure would be equal to PGH sub 1, knowing that this term here is going to be equal to 0. So we can eliminate that term completely. And then this is going to be plus 1/2 times rho times V sub 1 squared minus V sub 0, V naught squared, the original velocity squared. We're going to use the equation of continuity now. The volumetric flow rate is going to, of course, stay constant. And given this, we can say that pi r naught squared V naught squared equals pi r sub 1 squared V sub 1 squared. Pi's cancel out, of course, and we're getting that V naught, or the original velocity, will be r sub 1 squared times V sub 1 divided by r naught squared. And this is equaling d sub 1 squared times V sub 1 divided by d naught squared. So at this point, we can say that P sub O minus P sub ATM would be equal to the density times G H sub 1 plus 1/2 of rho, the density, V sub 1 squared, minus 1/2 times the density of D sub 1 squared divided by D sub 2 squared, D naught squared, D sub O squared, V sub 1 squared, rather V sub 1, and this entire thing, this entire quantity, would be squared. This is also, rather, we can further simplify and say that P naught equals, rather, P sub 0 minus P ATM equals PG and then here it would simply be times 1 minus D sub 1 to the 4th divided by D sub 2 to the 4th. So that's how we would simplify that. And at this point, we can apply Bernoulli's equation. So keep in mind this. And then we have to apply Bernoulli's equation again at levels 1 and 2. So P sub 1 plus rho, the density, G H sub 1 plus 1/2 of rho V sub 1 squared would be equal to P sub 2 plus PGH, rather PG, and then this would be the difference in height, so H sub 1 plus H sub 2, or rather the sum of the heights, plus 1/2 of PV2 squared. And so we know that V sub 1 squared will then be equal to 2 times GH sub 2. Here, the greatest part is that a lot of things cancel out. So this cancels out with this. We get that V sub 2 is completely eliminated. So again, yeah, and then each term here has the density term, so we can eliminate the density term. So we're getting this from that GH sub 1 plus 1/2 V sub 1 squared equals G H sub 1 plus H sub 2. So that's essentially how we were to find that the V sub 1 squared equals 2 times G H sub 2. And now we can use this in this equation. So we can finally say that P naught minus PATM equals PGH sub 1 plus 1/2 times PV1 squared, 1 minus D sub 1 to the 4th minus D sub 2 to the 4th. And this is going to equal PG times H sub 1 plus H sub 2 times 1 minus D sub 1 divided D sub 1 to the 4th divided by D sub 2 to the 4th. Oh, my apologies. This is actually not 2. I'm getting my subscripts confused. My apologies. Okay. And after that, then we can solve. So PO minus PATM would be equal to the density times the acceleration due to gravity, H sub 1, H sub 2, times 1 minus the ratio of the diameters to the 4th power. So this would be 10 to the 3rd kilograms per cubic meter times 9.8 meters per second squared times 1.1 meters plus 0.14 meters times 1 minus 0.5 to the 4th power. And we find that this difference in pressure is going to equal 12,066 pascals. So this would be our final answer after everything. So we have to relate it. We have to basically apply Bernoulli's equation at levels 0 and 1, and then at levels 1 and 2, relate them, and then find the difference in pressure. Again, that final answer, 12,066 pascals. That is the end of the solution. Thank you for watching.